Hi, this is the demo component of running Kafka on Kubernetes with Strimzi that we didn't include in the webinar, and I recorded separately. So we're going to go over the operational concerns section again, but actually do the demos this time. So when you install Strimzi, it's actually a two-step process. And this gets a lot of people tripped up in the beginning who expect when they install Strimzi, they get a running Kafka cluster, but that's not the case. You must first install the Strimzi Helm chart itself, which you can do by adding the Strimzi chart repository that's hosted on the Strimzi website, as you can see in these two command line instructions here. And then you can choose to install the latest operator, which is what gets installed if you don't specify a version. And if you want to override certain configuration of the chart, then you can go to the values YAML file of the chart and choose to override things like what namespaces to watch for cluster operators, to watch for Kafka CRDs to get created in, or other things like overriding the Docker image or repository to pull the actual Docker images for Strimzi. I'm not actually going to install Strimzi in this demo because I've already done that, but it really is as simple. All it will do is basically add a bunch of setup in the form of RBAC, kind of cluster roles, cluster role bindings, and we'll start a deployment for the cluster operator. But we will show a simple cluster getting created, and that's the second part. That's where you actually create a Kafka Kubernetes resource, and that's what creates the Kafka stateful set and the Zookeeper stateful set. So to do that, we're going to apply the simple Strimzi resource we looked at before. And just for the sake of completeness in this video, I'll just show that resource again. So this is a YAML resource. It's a Strimzi resource, a custom resource definition that gets installed with the Helm chart. It has a simple name, metadata name. It has configuration for the entity operators. So this includes the topic operator, and optionally, if you want to include the user operator, you can define that configuration as well. We're just using the defaults. The Kafka stanza here allows us to define the broker configuration. Again, this is just from the Apache Kafka documentation, all the standard broker config. The listeners are to set up the connection info for our brokers to listen for. So this can be network interfaces to bind to, whether or not to use client encryption using TLS. You can specify all that here. How many brokers you want. This is a standard Kubernetes pod resource request and limit setup. So you can set memory and CPU. We don't have CPU defined here, but you could do that. And then this is a storage section that defines both the storage class you want to use, how much memory we want to allocate for the volume we get provisioned. And then this is whether you want to use persistent volumes and persistent volume claims or that ephemeral mode. And then we have a similar configuration for the Zookeeper cluster. So let's create this cluster. So I have a terminal set up here. On the bottom pane, we are listening for, we're watching pods that get created in the Strimzi namespace. I'm in my little demo project here, so I'm going to apply the simple Strimzi resource. You'll see right away that pods start to get created in this namespace. So it creates them in a certain order. It's going to create Zookeeper first, because the brokers require this. We're only deploying one replica. And once this is ready, once the ready status goes to a 2, there's actually 2 containers that are running in this pod. And for each pod of the stateful sets, once that goes to 2 of 2, then we'll see Kafka startup, and there's the first Kafka pod. And in the initial example, we only have one Zookeeper node and one Kafka node. So to connect clients to this cluster, we just need to use the service that gets created with this cluster. So this is an example of a fully qualified Kubernetes service hosting to connect to the cluster we just created. So we're just going to break it down into its components. The first part is the name of the metadata name of the Kafka resource. And then several services are created per cluster. So in order to tell them apart from one another, we have this suffix of the host name called Kafka Bootstrap, and this is meant for the client connections to this cluster. The namespace, so if we have several, because we can create multiple Kafka clusters with Strimzi, it's possible to create the same cluster in multiple namespaces in sort of a multi-tenant kind of environment. So if we want to differentiate between those, then we need to fully qualify the host name. So we'd include the namespace that service is found in, and then this DNS suffix for completion, or for completeness sake. And then finally, a port. So 1992 is a default port for plain unencrypted connections. And then if you had set up TLS client encryption, you can use 1993. So let's connect a little client. So I'm going to create the topic that we saw before. So again, for completeness, let me just take a peek at this resource. The metadata name is the actual cluster name, or the topic name. And then this label associates it with an actual Strimzi cluster. And this is important when you have multiple Strimzi clusters deployed. Then we have the standard configuration, just partition numbers, number of partitions rather, and the replication factor. And then if you choose to, you can set as many topic level configurations as you want. And again, this can be found in the Apache Kafka docs. It's the same config you would normally apply to topics. So I'm going to run this little producer. And this is a Kafka producer that is just a bin script from the Apache Kafka release. And all it does is send records based on some kind of criteria, some settings we provided. So in this case, we're sending 5,000 or 1,000 records per second per partition. So you can see the details here, and this is just going to run indefinitely until we hit a arbitrary limit that we set. If you want more details, this is the actual script that's running. It's just using the Strimzi Kafka image and using the bin script that I just mentioned. So this is the Apache Kafka release script. The topic that we just created, we're going to use, and then various connection details for this performance test. And then finally, the actual service name for that service that we had created. So before rolling configuration updates, like we saw in the cluster operator section in the webinar, is a fairly simple procedure, one that you would expect. So the cluster operator is waiting for those Kafka resource changes. It's going to decide how to apply those changes to the Kafka cluster. So if it's a broker configuration, then all that's required is the generation of a new broker configuration and to apply that across all the brokers so it's consistent across the whole cluster. So to do that, once it sees a broker configuration change, it'll start from pod 0, delete that pod, and allow the stateful set to recreate it with a new broker configuration. So the Kafka pod will get created here in step 4, and that broker config that Apache Kafka relies on will get created. The Kafka process itself is started, and then we will wait for the readiness checks to go green before we move on to the next pod if there's another pod in the stateful set. So we're going to do a simple demonstration of this. So what I'm going to do is set this configuration here. This is just to allow or disallow topics from getting automatically created. When you have when you run a producer or consumer, if you connect it to a topic that doesn't exist, by default, Kafka will create that topic with the default configuration parameters, which is usually just, or the defaults are basically one partition and one replication factor. So it's not ideal, and you can easily lose track of topics if you don't set this to false. So we're going to set false, and we do that simply by modifying or patching the Kafka resource. So in this case, we're just going to edit the Kafka resource that we created, the previous step here. So this is the same YAML we saw before. It just has additional annotations and other fields that get added by Kubernetes and the Strimzi cluster operator. So here's the worker configuration section. So just add this new configuration, apply it. And this is issuing like a kubectl patch under the hood. It modifies it, and you can see right away that it terminated, or it's terminating that old Kafka pod. And once it's fully terminated, it will create the new pod. You can see it switched over to creating a new pod now. To scale brokers up, or out rather, is pretty simple. We just do the same procedure basically and modify the Kafka resource again. But instead of broker configuration, we're modifying this other field, spec Kafka replicas. So let's do that. So what I'm going to do is basically edit that resource again and go to the replicas field for the Kafka section of this custom resource and change this to 3. We do an apply. Now our Kafka resource has a desired configuration of 3 Kafka workers. So it's going to, the cluster operator is going to create the difference. So it's watching that Kafka resource, sees a change to that field, comes up with a reconciliation plan, which creates 2 additional pods in our stateful set. And this runs through just like how the initial deployment did. When you scale out or in, it's also a good idea to reassign or rebalance partitions across your new workers if you're scaling out, so that you distribute load across your cluster. If you want to scale in, that's more complicated, but it is possible by basically doing the opposite and reassigning partitions off of existing brokers onto brokers you intend to keep, and then reducing the replication factor. So the rolling broker upgrade we briefly discussed in the motivating example. So all we need to do is choose a version of Apache Kafka that is supported by Strimzi, so the destination version we want to upgrade to. And then all we need to do in most cases is just set that release version in the Kafka resource, and then Strimzi will automatically do the updates required in order to upgrade. So the first thing it will do behind the scenes is set that interbroker protocol version. So if you're doing a major Kafka upgrade, usually that version gets incremented, or there is a new protocol available. So Strimzi is smart enough to know that that's the case, and we'll pin the version to the current version, do a rolling update, upgrade all the pods with the new Kafka version, and then upgrade your interbroker protocol version. And then optionally, you can still manage the log message format version if you like, but Strimzi can't do this automatically for you because this requires coordination with your application developers that are writing apps to connect to your cluster. Broker replacement and movement, we discussed this in the webinar as well, so I won't get into detail, but basically what the process is if we want to move brokers around, maybe to different machines, for example, would be a common use case, then all you need to do, or the way to do it with zero downtime and to not oversaturate your network, is to first research the max bit rate per partition of your cluster. So this is probably close to your effective bit rate you get through your network adapters in an otherwise unused cluster. You find that bit rate, you move partitions off the brokers you want to replace, and you replace those brokers and have them bound to new kubelets, and then you do the opposite and rebalance partitions back to those new brokers. So these following slides are some hints on how to do that. So you can find the max bit rate using metrics in a controlled test. We can assign partitions off the brokers you want to replace using the Kafka reassign partitions bin script, or you can use various open source tools that make this a bit easier. And we apply the throttle that we discovered in point 2, or point 1 rather. We delete the pod and allow the Strimzi to recreate it. And then we reassign partitions back. Mirror Maker, if we want to set up disaster recovery or a multi-data center cluster where we have multiple Kafka clusters that are in synchronization with each other, then we can use the Mirror Maker application to do that, and Strimzi provides support for instrumenting it with a Kafka Mirror Maker CRD. So we have an example here of an active passive cluster, which basically means that you have one cluster that can be produced to and consumed from, and then you have a secondary cluster that can only be consumed from. If you want to have active consumers and producers in both clusters, that requires an active-active setup, which is a lot more complicated. So I'm just showing the diagram for an active-passive setup. So what we would do is we would create the Mirror Maker custom resource. The cluster operator would watch for it and deploy it. So I'll just show an example of the Mirror Maker resource. So you give it a name, you give it a Kafka version, and you can optionally have more than one replica setup of the Mirror Maker instance, and this would be good for better throughput. And then you just set your standard Mirror Maker configuration where you give it the source, basically consumer connection properties, and you set up the bootstrap servers for the producer. And this can be between any two Kafka clusters. It doesn't actually have to be between two Strimzi clusters. You would need one of Strimzi cluster in order to create the Mirror Maker itself. Yeah, you don't actually need to use Strimzi for the source or the sink. And then the whitelist configuration is just a whitelist on the topic names to actually synchronize. Strimzi supports Prometheus monitoring out of the box, and there's actually a Grafana dashboard that's in the project as well. We have our own dashboard that we manage with Lightbend platform that you get if you are a customer of ours. The way the monitoring works is there's a project called Prometheus JMX Exporter. JMX is the kind of default way to do monitoring for Java applications. So this allows us to, adding this dependency will automatically expose all the JMX metrics that we want to expose as Prometheus metrics, which are basically available through a web access point, or just a route off of the pod of the brokers and the Zookeeper nodes at this endpoint here. And then you set up a Prometheus server, which will either automatically scrape these based on based on a certain annotation that gets set on these pods, or you configure the Prometheus server to scrape it. And this acts like a basically a database for metrics that you can query and then use a tool like Grafana to visualize, if you like. So I'm going to show two things. I'm going to show a more realistic production Kafka resource. So this is an example of what we might create for our pipelines product. In fact, it is what we create for our pipelines product. So it has some different broker configuration. We don't have any, it's currently in an open mode. We don't have any listeners set up other than the defaults at this point. And then this is where the metrics are defined. And these are rules for that Prometheus JMX exporter project. So what it does is it takes a regular expression pattern for the JMX metrics, and then using groups that you define in that pattern, you can apply it to the Prometheus JMX, the Prometheus metrics that get generated on that endpoint. And you can also define labels as well, which are kind of like dimensions of the metric. And then we do the same thing for Zookeeper metrics as well. So let's take a peek at a Grafana dashboard that gets created. So here's a simple dashboard with the three brokers. This is an example of a pipelines Kafka cluster, and has all of the metrics available that we really care about to keep a Kafka cluster healthy. Such as how many under-replicated partitions there are, how many partitions are offline, the disk usage of all of our brokers, which is Kafka's Achilles heel, and then things like the throughputs in byte rates or messages per second, the consume rate and the producer rate, and then other metrics that tell us like how busy these brokers are. So in this case, you can tell that the thread pools are very underutilized at this point. So we can handle a lot more load if we need to. And that's the end of the demo part. So thank you for sticking around and watching this part. Thanks. Bye.